Hi, and you're officially welcome to another session of our POD discussion. In today's session, we are looking at singly linked lists, and we are going to try our best to understand the concept of linked list. Then we talk specifically about singly linked lists. Then eventually we look at implementation of singly linked lists. But more importantly, as I always say in our various sessions, that anytime a new concept is introduced, there are a few questions that you need to answer for you to be able to get around the concept. One, which is the very first one, will be to ask yourself, what is this concept? Okay, so at the end of the day, I mean, by the time we are done with this session, you should be able to tell us exactly what linked list is or singly linked list is. Then we'll also be interested in why do we even need to know about singly linked lists. We're also interested in when do we even get to use singly linked lists and how is it used. So if for nothing at all, we should have an idea about all these four questions. Once you've been able to cover these four questions, then it means you've covered the basis of singly linked list, and probably when you are given any questions around this, you'll be able to solve it. So now, let's talk about singly linked lists. I want to even start with the concept linked list. And I think this is an English word, linked list. In English, if I tell you a list is basically a collection of items, right? If you are going to the supermarket for shopping, probably you would make a list of the items that you are going to buy. And say you are going to buy a shoe, you are going to buy a backpack, okay? What else are you going to buy? Like whatever you are going to buy will form part of the list. So list is just a normal English way that we all understand. All right, bear with me. Usually I want to build on something that you know to connect it to what we are about to do, because I believe that's the easiest way for you to understand the concept. So let's go on. You know what a list is. Now we are saying a linked list. What does it mean for a list to be linked? All that it means is that there is a connection between the list. That is, one item or each item is connected to the other or to another in the list. That's how we should see it. If you say a list is linked, in this case, all that we are saying is that one or each item on that list has some sort of connection with another item in the same list. That is the only reason why we'll call it linked list. But the question is, what has this gotten to do with our programming and the things we are doing over here? That is a good question. We need to appreciate the fact that the linked list. Oh, sorry. I was trying to move my mouse where it's not going. Anyway, what we should know is the linked list is what we call a data structure. Okay, a data structure. And what data structure means is how we structure data that we store in the computer. How we structure it such that anytime we need to access it, it becomes easy for us to access it. And anytime we need to make some modifications to it, it becomes easy. So we are looking at storing data in a certain way such that using or accessing that data is very efficient and it can be done effectively. Okay, that is the goal of data structures. And we have actually talked about some of these data structures before. One of the data structures that we've talked about before is arrays. And if you remember correctly, we said that arrays are a collection of elements of the same data type. Okay, so elements of the same type is an array. Of the same type is an array. So let's build from here. Arrays are a collection of elements of the same type. So an array is actually a data structure. Why do we say so? Because it helps us store or put data in a particular order, and that storage or way that we are storing the data influences how we are able to access the data anytime we want it, how we are able to modify it and the likes. But depending on the particular data that you have, they may not always be suitable for storing in arrays. So what we know about arrays is that with an array, we have the collection of the data, but they have to be of the same data type, and we have to have an idea of how many data we are going to put in there. Okay, so we can go ahead and say that an array has a fixed size. Very important. You can say that an array in a way has a fixed size. And even before we use it, we have to be able to predict or know the exact size that our array is going to contain. So if I create an array of my scores for a particular exam, say one of them I got 80, one I got 82, one I got 85, one I got 92. Say these are the list of or the scores that I got for a particular exams that I sat for. The question is, yes, this is an array that we know of because it is a collection of what? Integers. The same data type being collected together in one data structure, that is an array. If I later realize that I forgot to add one score, the one that I got 65, I didn't add this, and I need to add this to this array, how am I going to do that? Remember that when you are declaring an array, the size of the array is fixed. So in this case, I would have said 1, 2, 3, 4. So I would have said that there are 4 elements in my array, using the square brackets. When declaring that this is an array, that's what I'm going to do, to tell myself that there are 4 elements, only for me to remember later that I left this score out. So how do I add it to this array? Unfortunately, there's no easy way to just go and add this member or this element to the array, because you predetermine the size of the array. The array has a fixed size. So the only way that we can solve this problem is we have to recreate a new array. So now we have to create a new array, maybe call it score1 and say it is 5 elements rather. Then we can go ahead and put 82, 85, 92 and say 65. This means that now we have created double of this. So maybe we'll go ahead and delete this. But you realize that this means that arrays are not efficient for storing data that will constantly change. It's also not efficient for storing data that we are going to be adding on, because it's not fast. Remember that I said with data structures, we are looking at the data that we have been given. How do we store it so that accessing or using that data becomes efficient? So as part of the whole data structure and algorithm things that you'll be learning, at one point in time, we are going to be learning the notations that are used to determine how efficiently this can be accessed. So we will talk about, not in this particular class, but we will definitely look at it sometime to come, what we call time complexity and space complexity. And in simple terms, what these two mean is that we are looking at how much space is this data going to occupy in our memory. Then how much time will it take us to access any element in this array, or to insert an element into this, not array, I mean data structure in general. So when we learn about space and time complexity, that will help us choose the best data structure at any point in time. So if you have a case, you are going to build an app, you are going to do a project, you would have to come up and think about it. So assuming that you are building an app that keeps scores of the students what results from various exams, the question you ask yourself is, should I use an array to store each student's results? Or what type of data structure should I use to store each student's results? That is where you begin to question yourself. If I use an array, what will be the space complexity? What will be the time complexity? And you compare it against the others. Then you end up choosing the one which is more efficient. For now, we are not concerning ourselves with space and time complexity. But what you realize with the example I gave is that adding onto an array is not an easy task. So we need to be able to have a particular data structure that we can easily add something onto. And that is what linked list comes in. That is where linked list comes in. So a linked list is not so different from the idea of an array because it's still a collection of data. However, it has a number of differences from that of an array. How different are they? In an array, when we take a look at how it is stored in the computer memory, which when we're discussing memories, even when we're discussing arrays, we talked extensively about it. So if you weren't here when we're discussing arrays, you can go back. The video is available on YouTube. Go back and watch it to get a full understanding of this topic. Okay, so with the scores that we had, say 80, 82, 87, 92, 65, let's assume these were the scores. In the memory, these are stored in contiguous memory locations. That is, inside the memory, they follow each other. So by knowing this, I can predict exactly where this is going to be. By knowing this, I can predict exactly where, in fact, just by knowing the first one, I can predict where each of these members is going to be, or the memory location for each of these members can be predicted. Because in the memory, an array is stored in a contiguous order, that is, they follow each other. And that is one of the major reasons why working with arrays too isn't that easy. With the idea of the linked list, the difference is that if you have all these cores put in a linked list, what actually happens is that they are linked to each other, not necessarily in that contiguous memory location. So any of them can be found anywhere in the memory. The only thing is that each of them, or each member, has a connection to the adjacent member. So here we can have 80 here in memory, we can have 82 here, we can have 92 here, 65 here, assuming this is how the memory is. Okay, the only important thing is that each member is what's linked. So let's say this is the link. 80 is connected to 82, 82 is connected to 92, 92 is connected to 65. I think I left out 87. So let's put 87 here, something like this. So all that we care to know is the fact that they are available in the memory and each of them has some sort of connection to the next one. So that's the basic difference between an array. With an array, they are put in continuous order in the memory. That is, in the memory, one follows the other. But with a linked list, it is not like that. We really don't care where exactly they are located in the computer's memory. All we care about is the fact that if you are adjacent to me, I have a connection to you. And in that same order. Okay, so let's take a look at how the linked list will be represented. In order to make room for this connection, okay, each linked list item in the linked list, this we say an item in an array, okay. This is how we call an item in the array, or an element of the array, or a member of the array. In the same way, we are referring to each element in the linked list, or each member of the linked list. We can call it like that. It's presented in this format. So each member in the linked list is known as a node. Pay attention to that. Each member in the linked list is called what? A node. And each node has two parts in single linked list. That's what we are discussing today, singly linked list. Each node in a singly linked list has just two parts. The first part is where the data itself will be stored. So just like in an array, we have the data being stored here. But it has another part where a pointer or address will be stored. What is this address? This address is the address of the adjacent node. So if there are two nodes that are adjacent, one will keep the address of the other. Okay, and it goes in only one direction. So it's just in the forward direction. So this node in particular will store the address of the next node. The next node will store the address of the next one in that order. So let's take a look at this. If you have three nodes, say node A, node B, and node C. Say these are the nodes that we have. What is happening is that each node has two parts, as I said earlier. There is the data part. This is where the actual data that you are keeping will be stored. And this is where, okay, this one too, the data will be stored here, and this, the data will be stored here. Did I mention that the second part is the address? So here, this part will have the address of node B stored here. So let's say B address will be stored here. In the same way here, we will have C address. But one peculiar thing is that with the last node or the last member of a linked list, a singly linked list, it has no connection with an adjacent node because there is no other adjacent node. There is no other node after it. For that matter, we put now, or we say a pointer to now. Okay, so this will connect to that. And once it is a forward connection like that, this is what makes it a singly linked list. We can go only one direction. We can't go the backwards direction. So it's always what? Forward. It's always a forward movement. You can move from here to here. Very important. During the course of my reading, I came across something which I think I should share before we delve more into singly linked lists. That's a practical application of linked lists, and we should be concerned about what's the advantage of linked lists over arrays. So I've already mentioned the fact that with arrays, we have a fixed size. With linked lists, you don't need to even know the size. This is done dynamically, okay? So with linked lists, you only create the list dynamically. And that means that you can add on anytime you want, even during runtime. But with an array, you have to detect the size of the array during compilation. Okay, so that is one of them. Then I also mentioned the fact that removing items or adding items is quite difficult. Adding items to an array is quite difficult, unlike in a linked list, which we will see soon. And the other thing too is that even with an array that you have enough space, okay, let me go back to arrays. I want to explain that example that I came across, but before I'll be able to explain it well for you to understand, I need to make you understand this one. Let's assume that I predicted that the array may take more elements than I can imagine right now, so I made room for it. So assuming this array actually took only 4 members, okay, 87, 95. It has only 4 members, but I decided to create 5 members. Okay, so maybe when I was creating scores, I did it scores of 5 instead of 4, because I knew that, oh, there is a possibility that one more will be added. Now the question is, if I realize that I have to add that my 65, but I need to put 65 in front here, that is in front, or make 65 the first element of the array. The question is, how is that going to be possible? And this, when you are working with arrays, is a very expensive thing to do, because before we can come and put this 65 in the front here, we would have to move each of these. So I have to move 95 here, 95 will come here, 87 will come here, 82 will come here, then 80 will come here before I can put 65 here. That is a very costly thing to do, because it's going to take time. You're not going to move this here, move this here, assuming if there are thousands of these memory elements, you have to move each of them before you get the space in front there to also what? Fill it up. If you need to also delete something, assuming now I want to delete this 65, it was a mistake, it doesn't have to be there. After I delete it, I can't leave this empty, so I now have to move this here, move this, move this, move this to replace it. That is a very costly thing to do. So one of the easiest ways to solve that problem is to use linked list, which we are going to see the implementation, how easy it is to delete or insert elements into a list. So if you are working on any projects which will require that you need fast insertion or fast deletion of items, then arrays are not a go-to. It's not the go-to data structure if your interest is in fast insertion and fast deletion. And also, if your interest is in being able to dynamically allocate space for something, or adding on to the list when you are in runtime, when the program is already running, then using an array is not the right thing to do. So now back to the example I was going to give, what I said I read about. Let's look at a platform like Instagram. It was quite interesting when I was reading it, and it made it more practical. I think most of the times the concepts that we read looks a bit abstract, okay? So even though some of them are abstract, when you get to know how they are applied practically, it makes more sense. Let's assume that you were the one who was contracted to build Instagram. All of us here know that Instagram, you post pictures and videos. Let's just even restrict ourselves to pictures, okay? So you are going to have a collection of what? Images. So with your basic knowledge in programming, if they ask you, how are we going to be storing these images? They are of the same type. Let's assume that they are of the same type. How are you going to store these images? The first thing that may come into your mind is that, oh, we can use arrays. Since they are of the same type, we can use arrays to store them. And that is not wrong. You can use arrays to store your images because they are of the same type. Because at the end of the day, if you write your array, what you may need is probably just the URL for each of the images. So in here, you save the URL for image 1, URL for image 2, URL for image 3 in here, and in that order. But ask yourself, will it be the most efficient way to store these images? How we are going to answer that question is, how do we even intend to use these Instagram images? If when I'm building an app, I have to put the images in there and nothing is going to be updated, that is all. Like once I build the app, I've added it, then using an array is perfect, because I would have determined how many images do I want to put in here. Oh, I want only 4 images. So let me create an array of 4 images, then I'll put them in there. But unfortunately, for Instagram, we need to allow the end user that is doing runtime. The program is already run, the app is available, the user is using it, and we don't know how many images the person is going to add. The question is, how many images have you added to your Instagram account since you created it? Do you know the programmer who was programming? Did the person know that you were going to put that number of images there so that they made room for it? No. That will not make it the most efficient method. And even if the person decided that, okay, maybe people will put a lot of images, so let me make room for a huge array that can take as many images as possible. The next question becomes your Instagram feed. What happens is that anytime you post a new image, the new image will come to the top. If any of you here use Instagram, I believe you know what I'm talking about. The new image comes to the top. Okay, anytime you post an image, the new one will always come to the top. So the question is, if you use an array to store it, then it means that anytime you post a new image, we have to, assuming the person left enough room to contain all the images. Who has unmuted? I think there is noise coming from the what is that? Okay, sorry about that. So with the example I'm giving, assuming the person made room for as much images that each account can post, okay, probably after a certain number of images they will delete it, so you have a certain number of images, so they use an array, and that's fine. But the question is, how do I force all the new or the incoming images to the front? Just as I showed you earlier, it means that before I put the new image there, I have to move this previous image to the back, move this to the back, move this to the back, then make room for a new one. So every second, you just imagine how many images are uploaded to Instagram per second. If you like, you can just Google it and find out. So for each second, we have to be doing all this. Imagine if the person has already posted like thousands of images. You have to shift all the 1,000 just to make room for one new image. Do you think it will be the most efficient way to store these images? And that is an absolute big no. Okay, so I've mentioned that if your interest is in fast insertion or deletion of items from a list, arrays are not your data structure of choice. So that is where the linked list comes in. So with the Instagram images, we can perceive it to be in the form of singly linked list, where the new one, the old one is connected to the new one in this order. Okay, so there is a connection between them, and each of them is about the other. And anytime you bring a new element, they will be put at the top. Okay, so that's like a practical. We can't really say that's what they used in Instagram, building Instagram, because there are other data structures that can also possibly be used. But this is the ideology behind it, and it could be the solution. In fact, it is one of the solutions whenever you need, your interest is in fast insertion. Whenever your interest is in being able to what, like insert an item fast, it is one of the options that you go with. So now we can presume that with our knowledge of data structures so far, the Instagram algorithm or the structure that was used is a singly linked list structure. And the reason why we are saying so is because it makes room for fast insertion. Okay, so now let's delve more into singly linked list. So with a singly linked list, there are two major things that you need to be aware of. Okay, as I drew, so let me draw it again. Let's assume we have 3 nodes in this list. 3 nodes. I said each member of the list is called a node. Okay, so let's say this is node A, node B, node C, and each node is divided into 2 parts. One part is the data part, the other is the address of the nest. Is the address of the next part. That is the so the first part here is what? The data, whatever data you're storing. So in this case of Instagram, we have the images here. Then this next one contains address of the adjacent image. The image here, address of the adjacent image. Then this one will point to now. So there is nothing here. So the moment you bring in a new image, the new image will be filled here. Okay. But what I need you to pay attention to is this. Now, then how do we know that this is the beginning of a linked list? Okay, there is a pointer, which is a very important pointer, and we've talked about pointers extensively. So there is a pointer to the first address in the list. We call it the head. So the pointer to the first item in the list is called the head. So before we proceed, you need to know what the head is and what this is. The null is what gives us an idea of what the end. So this is the end node. This here is the first node. So the first node is the node that the head points to. Then the end node is the node that points to now. Remember that. We are going in only one direction for a singly linked list. That is what makes it singly. The connection is just one direction, forward direction. Okay? The head is a pointer. Please pay attention to that. The head is just a pointer, not a node. It's a pointer pointing to a node. I'm repeating this because when we begin doing the implementation, that is where some of you may end up being confused if you don't get this basis. So the head is what? A pointer, not a node. What type of pointer is the head? The head is a pointer to a node. Great. Then this A here is a node in itself, B is a node in itself, C is a node in itself, but C is pointing to now. So we say C is the end node because it points to now. We say A is the first node because it is the node that head points to. So at any point in time, where head points to is the first node. That means that anytime I need to know about what this linked list contains, all I need is head. So head is like the password to the list. If you want to get into the list, all you need is head. Without head, you can't get access to the list. Because head is what will tell you that, oh, these set of items you are looking for, they are in this location. Go here, go to room 151. That's where I kept them. That's what head is doing. So anytime you are looking for a list that has been created, a singly linked list that has been created, just ask your head. Head is a pointer. It will point to you, oh, go here. When you go into the memory, look for this specific location. That is where the first item is. Once you find the first item also has a link to the second item. So the first item will now tell you that, oh, the second one is rather in this direction. So go there and look for it. You find the second one, it will also tell you that, oh, the third one is here. Go and find it. By the time you meet the third one is not pointing anywhere because, oh, I am the last one. I hope that makes sense. So that is the concept of the singly linked list. Any questions so far? Any questions so far?
Look, I want to know how does the node have both the data and the address at the same time?
Okay, sure. All right. So when we take a look at how nodes or how linked lists are implemented in a programming language, you realize that one data structure that we've talked about earlier is what we call, in C in particular, is what we call structs or structures. Okay, you remember this? We've talked extensively about it earlier. And in fact, when we're doing it too, I think I spent a lot of time on the theory. And going forward, when we have started talking about most of these data structures, we may be making references to it. So if you have forgotten what they are, you'd always have to go back and revise them. So the advantage that we saw struct giving us was the fact that it helps us put a collection of items that are not of the same, not necessarily of the same type, like multiple items. Okay, so unlike arrays, we talked about arrays as a collection of items of the same type, but they have to be of the same type. Okay, what if I want to collect, let's say, integers, character, character pointer, float together? How is this possible? You can use a struct to collect those ones. So the nodes are implemented as structs. That means that each node can take multiple items. So for this node struct, let's say we create a struct called node. Okay, this is how we are going to create it, something like this. Then inside it, we may have an integer called scores. Okay, that's the score the person got. Then we may also be interested in any other thing. It could be the person's name. So let's say a character pointer. Okay, a character pointer, or let me say name. Then pass. I'm trying to delete this asterisk. Name and pass, say 50 here. Then the last thing I'm going to do is going to be a pointer. So this is how I'm able to create. I'm including within each node, I'm including an integer, a string, and a pointer. Then this particular pointer is going to be of type struct node. What does this mean? It means that this pointer is a pointer to this node that we have created. That's what makes it interesting. So this is just a pointer. I can call this next. That means that I'm pointing to the next. So anytime I create a node, let's say I create node 1, or in the example we give, node A. Node A is going to have data of, let's say, score. So say 80, then the name of the person, say Obed. Obed scored 80. Then the next thing that it has is a pointer. So a hexadecimal figure that will probably end with, say, 72. So node A contains all this. I hope you are getting the concept. Node A contains all this. That is what we have created. Then we can go ahead and create node B2. Node B will contain, say, 95. And the name is Ima. Then the pointer is, say, this ending with 15. Okay? So this is how the nodes are implemented in the memory. We are using struct to help each node be able to put together a collection of data. It depends on the data we are putting together. So for Instagram, for instance, each node that we have will contain the image, or what we will call the image URL. That is a link to the image that the person has uploaded. Then it will contain the caption. Okay, then probably metadata about the image, like upload time, upload date, and things. All of these will be captured as part of the node. But more importantly, we will have a node as a pointer to a node. Okay, which in our case we can call next. So this will point to the next one. So for each node on Instagram, that is for each feed item that you see in the structure, like later we'll learn about databases, and all of these will probably make sense somewhere, how they are stored in a database and how you get there. But for now, look at the data structures we are talking about. If you are using linked for this implementation, then this is what it looks like. Each item contains the image URL, it contains a caption, it contains, so you will dynamically allocate enough space for this to contain them. But what makes this peculiar is the fact that it has a connection to the next node. That's the only thing that makes it peculiar, because we've already discussed structs or structures in C. So you can create structure out of anything for anything that you want. But what makes a structure a linked list, or in this specific case, a singly linked list, is the fact that each structure has a pointer to the next node, and the very last one has a pointer to now. Ima, are you answered?
Yes, yes.
Okay. Any other question? Any other question? Okay. So let me quickly go over this, then we'll turn to the code for us to do some coding. Go over how the singly linked list is implemented. Remember that in your mind, in fact, let me just mention this. Anytime you have a question on linked list, it's easier solved when you draw the structure in your mind, or just draw it out. Like, okay, this is node A. We've created node A, and node A contains. So if you are using the Instagram example, this space that has been allocated, don't see it as just 1 byte. Like, it could be as much as possible. It depends on the size of the structure that you created. Okay, so this space here will be containing the image URL. It will contain the metadata, the data was published, the caption, and everything. All of them will be kept in a particular space here. Okay, so the computer would allocate a given space that will be enough to contain all this information. Then we have this other part that contains what? The pointer. So it contains a pointer to the next node. The next node in our case would be node B. Node B also has the picture stuff, so the image details here and the caption. Then it also contains a pointer to the next one. Okay, so anytime you are given a question on linked list, try and draw out this thing and try to understand the flow. Okay, and this will probably point to now. Then image details here. So what I've said is that to implement a node, to create a node, we create a new data type. If you remember from our lesson on struct, I said struct allows us to create a new data type. So in this case, we can call it struct anything at all we want. We can give it that name. So I can call it struct Obed. But to make things easy for us to understand, it's recommended that you call it struct node. You call it struct node. By calling it struct node, it just clicks that, oh yeah, you are dealing with a node. Okay, but it doesn't mean you always have to call it node. You can call it anything you want, but it's a struct, and this is how structs are created in this way. So it can contain only one item, say age. We are just going to be keeping age of people. Then the next thing is struct node pointer. This is just telling you that we are creating a pointer to a node, and we are calling that next. You can call it anything also, but when you call it next, it makes sense. Like, you know that, oh, okay, this is a pointer to the next. So it makes sense. You can decide, like, just as we were calling all our pointers, like during our PLD session, I call all the pointers PT something. You can decide to call it PT something in order not to confuse yourself, to know that it is a pointer, but you can equally leave it as next, like that. Okay. So this is how a node is declared, or let me say not declared, the template of a node is created. So from our lesson on struct, I told you that this is creating a template so that anytime you declare a new node, it knows exactly, or a new struct, it knows exactly the format to take. So if I want to create node A, node A is going to take, let's say, age 56. Node B is going to take age 72. Node C is going to take age 45. If I'm going to create this, I would first have to come up with this template. So I have this template. Then after that template, I need to go ahead and declare a node. So to declare a node, I'm going to call struct node, because that's the new data type that I'm working with, struct node. Then give my node a name. So in this case, I'll call my node A. Just by doing this, I've declared that I need a node of this nature. This is the template I'm going to build my node from. Okay. So the computer is now going to start making room to create the node, but I need to give it space. Like in the memory, where should this node be stored? And we have learned how we create our own space in the memory to put something that we want there. So what do you think? We have to use dynamic memory allocation. Which function will we use to create a space for our node? Yes, anyone? Which function in C will you use to create or generate space for this node that you are about to create? Yes, anyone?
malloc.
Thank you. So we can use malloc to allocate that space that we want. That's simple. We have declared that, oh, we need a node called A, and that node will contain what? Age and a pointer to maybe the next node. So we have to use malloc to create or allocate space for this node that we are creating. How will malloc know the size of space to leave? Are you just going to write something there and say, oh, 4, so that it allocates 4 bytes? No. Malloc will have to determine the size of the node we are about to create. Okay, for that matter, we can pass malloc, then we say size of what? Struct node. So we are passing this whole structure. Okay, let malloc determine what is the size of the structure that I created, because I need one of them. I need to create, this is just a template, okay? But now I need to create an actual data from this template. So I'm giving malloc, this is my template. You determine the size of this template and let me know. Once you get the size, so let's assume that malloc goes through this and say, oh, this is 4 bytes, this is 8 bytes, and say, okay, 12 bytes. It's going to allocate space for 12 bytes. Then now your node has enough space to go and occupy. So within this 12 bytes, we will have the integer occupying, say, the 4 bytes, the pointer occupying, say, the 8 bytes. That is how it works. I hope it's going well. So we begin by creating the template, which is a structure. Then you declare the node. After declaring the node, you now have to allocate memory space for it. You have to allocate memory space for it. Even before you start passing the values to the node. Let me take that again. We'll soon be going to the code editor, so I want you to understand this. The first thing is what? Create your templates. Okay, create a template for the nodes. For the nodes. So that's the very first thing. That Samuel, do you want to ask a question? Resilient Samuel, do you want to ask a question? Otherwise, you have to mute yourself. Like, I'm getting feedback from your end. Thank you. Sorry about that, but any small noise irritates me, that's why. Okay, so we create a template for the nodes. That's the first thing that we do. Then the second thing we do is we declare a node. So give your node a name. That is you declaring it. Declare a node. Then after declaring the node, yeah, kindly hold on, coming. Kindly hold on for me. Declare a node. After declaring a node, you allocate space for that node. Okay, so memory space, allocate memory space for that node. For that node. Then the next thing you do is pass the values to it. So now you can pass values to the node, or let me say assign values to the node. The right word will be assign. Yes, Mary. Assign.
Okay. I just wanted to ask my question before you go too far.
Okay.
In the structs, you can have maybe I don't know how to put it. The way you have the integer and then the pointer to the node. You understand? You said that a node has the pointer and then the data uh,
Yeah.
value or
Right.
something. Can you have like, okay, maybe in the first node you have an integer and then pointer, and then the next node will be maybe a character and a pointer. Can you have something like that?
No.
Okay.
No, because we have created a template that each node should follow.
Okay,
Do you
I asked
get
this
it?
question because
Mm-hmm.
when you're grouping your structs, you can have integer, you can have character, and I see that you said struct node.
Yeah.
Yeah, so that's what I'm asking.
Okay. Okay. So the whole thing is that at the end of the day, we are working with a template. Okay. We are working with a template. Like with an Instagram example, each image comes with the image name, the URL, the meta description, the caption. Okay. So you can't have like talking about images here. Then the other thing is the next item in the thing is something else. Maybe it could be possible, but I haven't seen any implementation like that. Because I'm now thinking image and videos, they can also be linked. But I haven't really seen anything like that. So I can't really say much about it. But for what I know, we are going to create one template that we are going to use throughout. So
Oh,
I think now thinking about it, it's going to be possible because we can implement that. We can create a new struct, a new template and use it. But so far with all the things I've come across where we are using it, I haven't really found a need to create multiple struct templates and use them to create different nodes and still connect them. I haven't really found a need for it. So maybe if there is need for it, that can be implemented. I'm thinking so. Yeah.
okay, thank you.
You're welcome. All right. Any other question? Okay, good. So these are the four things that we need to update now. The four things. Very important. First, we need to have a template. After we have gotten a template, so once we have created a template, the template is general. We can use one template to create thousands of nodes, okay? So that's like the mother thing that we'll do. Then for each of the node that we are going to create, we are going to do this. For each of the nodes that we are going to create, we are going to do this. We are going to declare the node, give the node a name and the type. Let's know that it's actually a node of this particular type. Then you are going to allocate memory space for it. Okay. Then you are going to assign values to it. After you have done all these things, another important thing that you should remember is that we can only identify a linked list with the help of a head. So that means that we always also have to pay attention to this pointer called a head. And we said that the pointer points to the first item in your list. So if and only if you have been able to create this node and say this node, you want this node to be the first thing, let's say node A. You want node A to be the first member of that your list. Then you have to now assign the value of node A, I mean the address of node A to head. Then the time when you get to the very last node, you have to assign that last node to what point to now. Exactly. I think it's high time I launched the editor so that we explain some of this practically.
So Doc, that means it's a must that there must be a head.
Yes, you can't have a linked list without a head.
Okay.
So always you have to have a head. Okay. Give me a few seconds. I'm trying to launch my virtual machine. Yes. Someone speaking?
All right, I just wanted to ask where in the memory, which memory are we saving these nodes? Is it on the RAM or on the hard disk?
Okay, sure. So when we talked about what was that session? I think dynamic memory allocation, the very first lesson that we did, I explained how all those things interplay. But these are things that you are generating during runtime. So it is using the RAM. You are using malloc to generate memory here. So it is with the RAM, not the hard disk. Anytime you have a program, before the program runs, okay, the program is moved because these files that we are going to create, when we launch, we write our code, they are going to be on our hard disk. That's where we are storing them. But the moment we begin to run it, they are moved onto the RAM. So instead of calling it a program, once they are on the RAM, we now call it a process. It becomes a process. Okay, so it is when the process is running that we are actually going to allocate the space. So we are allocating the space on the RAM. I hope you are answered. This my
Right, yeah, thanks.
okay, welcome. All right. Okay. So let's call this call it, what are we doing? Singly linked lists PLD. This is too long. Okay. Singly linked PLD. Then let's see the into singly linked PLD. Then open this. Okay. Call this. What are we about to do? So let's just call it node.c. Tony, do you have a question?
Yes, Doctor, I have a question.
Okay.
Yeah, sorry, I'm seeing you opening a visual code on. Yeah, because I tried writing a C program on my visual code here on my Windows machine and was having all these series of errors. I don't know what the problem might be. And now I'm not seeing. Are you running this on your virtual machine on Ubuntu?
Yeah, I am.
Oh, okay.
But that's not a problem. You need to be able to run C on VS Code. You need an extension. See, now it has picked the language that I'm working on, C. So you need to have that extension. I think it's called C++ extension also. So when you click here, extensions, you can set yes. There's it. Okay, I think this is not the one I installed, but one of these, any one of these C++ extensions. Once you have it installed, you'll be able to use it.
Okay, thank you.
You're welcome. All right. So basically, I think there's one thing I needed to. We've talked about it, but let me go back and summarize this thing, which is very important. The things that we are using. Remember that in talking about this, we are using structs So it means that if you are forgotten what structs are, you have to go back and revise that. We are talking about dynamic memory allocation. Okay, dynamic memory allocation, specifically malloc and free. We'll be using those ones a lot. So it means if you are forgotten this, you also have to go back to it. Then, more importantly, the concept of pointers. So without these three things, especially this one, okay, especially this one, without them, you have to go back and go and do some form of revision before you come to really understand this. And good for us. I mean, for ALS, we are taking a break from C, actually, what we have done right now. Now, after the project we have at hand, when we come back, we are going to Python. That means that by the time you're done with this project and the break that we will be given, you have to go back and revise everything we've talked about C. Okay, then we'll move on to Python. What is important is just understand the concept, what this means, just understand the concept. And if possible, try doing some of the exercises we've done previously or other projects. Try writing simple programs with it, and that will bring you up to speed. Okay, then we can now move on to the new programming language, and we are going to apply most of the concepts we've learned here in the new programming language. So hopefully by the time we get there, you have covered the basics, understanding the concepts, then it becomes easier for you. A lot of people are saying Python is easy, but if you don't understand the basic concept, it's similar. The syntax isn't as huge as C requires of us, but it is basically about understanding the concept. Do you know arrays? Because we are going to be dealing with arrays in Python. We are going to be dealing with lists. We are going to be dealing with even different types of data structures. There is dictionary, there is tuples. All of these things, we'll be talking about them. But when we're talking about arrays in C, did you take them serious? Did you understand it? Otherwise, you are still going to waste time trying to understand it. So that was just by the way. So let's go back in order to understand singly linked lists. And I've said that linked list is not a concept for only C programming. We'll use it in any other programming language you are using. So have a fair knowledge on these things. Now let's go. I went back because I have to come and write this include statement. What do you think I need to include apart from stdio? stdio.h. What other thing do you think I should include? Is anyone with a suggestion based on the things that I said we require? Anyone? Yes.
I think malloc would require standard lib.
Okay, thank you very much. So yes, so we need stdlib.h because we are going to use malloc. So if you have forgotten, how will you be able to implement this? It means you can't do it. So that's why it's important for us to go back and go and do it. Say int main, and let's say void. Okay. So we are going to write everything within the main. Or even before the main, let's write our structure up here. Say define structs node, and let it take what is it going to take? Okay, for now let's just pass age. Okay, we just want to store age of people. Then the next thing is structs node pointer. So this is pointer to a node. Then we call it next. Great. And here. Okay. Remember that when we're learning structs too, we learned about type def. So you could actually use type def. What I've seen people do is they use type def to create like an alias for this struct, call it say node. That means that anytime you call node, you'll be creating something of this nature. So if you have forgotten about type def, go and check it out. Otherwise, you can go ahead and use it like that. All right. Now we've created a template. Remember, that's what I said. This is what a template for our nodes. Then when we come in here, if we want to use it, we have to, let's say, declare. Okay, so that was the first thing. Let me go back to my screen and show you. The first thing I talked about was create a template, which we have done. Then after creating a template, you declare a node. So that's what we are about to do. Declare a node, or declare, you can declare even all the nodes together, all nodes. Okay, but if you want, you can also declare them one by one. So let's do declare a node. How do we declare a node? What is the type of the node? It's a struct node, but what are we declaring? We're declaring a pointer to that node. Okay, it's a pointer to that node. That's what we are declaring. Please pay attention. A pointer to that node. So node, call it node A. It will make sense soon. A pointer to the node. Why must it be a pointer to the node? Do you remember the outcome of malloc? What does malloc return? Anyone? What does malloc return? It returns a pointer. Good. So the next step is for us to allocate space using malloc. And malloc is going to return a pointer. So we need to assign a pointer to it. For that matter, let's say allocate memory for the node. Okay. So how do we do that? We have created a pointer called A, and we are going to assign the value that malloc presents to it. Malloc and size of what? Struct node, because that's the data type that we are using. But since this malloc is going to return a void pointer, okay, so we can cast it to this struct type that we are looking for, struct node pointer. We want you to return a struct node pointer because this is a struct node pointer. What this is actually doing is that malloc is going to create enough space to contain the new node that we are creating. It's going to make enough space for it, but it's just returning a pointer where we will be able to use to access it. That is what we are getting here. Now, after allocating space, what's the next thing we do? We assign values to the node. So let's assign value to the first node we have created. Assign values, assign value to the. And how do we do that? We said that this particular node that we have created, that's what it has. Two parts. It has the data part and the pointer part, or the address part. So now, how do we assign a value to this specific node? Okay, this node is of type this, and it is a pointer. And if you remember from our lesson on struct, remember that we introduced this particular sign pointing to, or pointer to, symbol, okay, which we can use to access the members of a struct. So the member variable of a struct can be accessed when we are using a pointer. You can use this, or you can use the dot notation but with the asterisk before it. That's also possible, except that it's not very convenient this way, so we prefer to go this route. Then we can now go ahead and say this is equal to, let's assign an age, say 67. That's the age we are assigning to it. The next thing that we will need to assign will be what? Will be an address. If it is only one node and that is the end, then the address will have to be now. So this next is the address. So if we are to assign it to now, this is how it's going to be. So this is how we create a linked list with just one element. But even before we end it, we now have to tell the create a head. Okay, so let me say create a head. That is how we are going to be able to identify it. And the head is simply just a pointer of what type? Of struct node type. It also points to a node of this type, struct node. So you can go ahead and add it here during your declaration. You can have something like this here. Okay, because it's the same data type. Otherwise, you can also decide to do a declaration by itself and copy this whole thing and put it on another line and call this head. Okay, this is also acceptable. Now that we have the head, all that we need to do is that this head should point to the first element in our our list. And the first element in the list as we have right now is node A. Node A is the first member. Remember that node A, as we have called it, even though it is a node that contains multiple things, it is only when you come deep into it that you get those things. But the time you call just node A is a pointer, is an address. So if I come here and I say head is equal to node A, you have to understand what I've just done. Node A is the pointer that malloc returned. So head is the pointer. If I assign a value of node A to head, that is the right thing to do. I hope you get it. Node A in itself is what? A pointer. Because when we declared it as a pointer to this data type, struct node data type. Then if you are not convinced from there, this should be struct. If you are not convinced from there, then you should also remember that malloc returns a pointer. This means that whatever node A is actually a pointer. And we have said that head is a pointer to the first node. So this is how we'll make head point to node A. So by doing this, we have created a single linked list with just one member. Now let's say we want 3 members, okay? The examples we've been doing so far, like with the drawing, I've been drawing 3. So let's go ahead and declare 3 of them, comma, node B, comma, node C. Sorry. Okay. Then it means that we have to allocate space for all of them as well. Very important. So this will become node B, and this will become what? Node C. Then we have to assign values to them. To assign values to them, let's work with the data values, okay? So let's say assign data values to the nodes. So we'll have this. Node B, then we pass the value of node B, say it is 47, okay? Then we come to node C and pass the value, say 35, but this should be C, node C. Great. Now the next comment, let's focus on passing the addresses. Please pay attention to this part. We are assigning address values to the nodes. So here it will be, it can't be now here. A is the first pointer. Okay, so A next should point to the second, node A is the first member of the list. So node A next should point to B. B should point to C, then C will point to now. So this is how you write it. Node B, because node B is a pointer in itself. So we just use the name node B. We don't need to use node B that's this sign points to next. No. Once you call node B, you are calling that node its address. So we are just passing node B's address towards node A next. Maybe I should go back and explain what is happening here. So what we have done is that, we created 3 nodes. We have created A, we have created B, and we have created C. Okay, but the way we create these things, the name itself is a what? A pointer. The name itself is the pointer. So anywhere in your program where you use just the name of a node, remember that it is what? A pointer. Even though it is representing the node, it is representing the node because we can use that pointer to access the members of the node. But by standing on its own, it is just a pointer. That tells us that, okay, when you go into the memory location, A is where you find these values. They are here. B is here. C is there. Okay, that is exactly what we have done. And now what we have also done is we are passing the values in here. That's what we did initially. Did I change this to 47? Then this to say 35. Okay, and we are about to fill this. So we want this to point to this node. Once it's going to point to this node, the address is what? B. I mean, it's going to point to this whole node. Okay, the address of this node is B. So we should put B here. Then this node 2 should point to this whole node. And the address of this whole node is C. So we'll put C here. But C is not pointing to any other node. So here will be now. That is what we are trying to achieve with the code that we are writing. So node A, let me copy the whole thing. Node A here will point to node B. I mean, node A next will point to node B. Then node B next will point to node C. Then node C next, since it is not connected to any other one, will point towards now, because that is the last member of the list. So by doing this, we have created, remember this, head has to always point to the first element. So node A in our example is the first element. For that matter, this is how we present it. So what we have done right now is that we have created a linked list with 3 members. Remember, I'm not doing everything that you would have to do. I'm trying to just explain the concept of linked list and its implementation. Because the ideal thing is that for each of these, we have to check that it doesn't return now. If it returns now, then there's a problem. So we either close the program or print out an error message. But I'm not doing that. I'm just using it to explain the concept. So let's go over. In creating our nodes, what do? The first thing is we generate a template for the nodes. After generating a template for the nodes, we declare the nodes that we are going to create. Then we should also declare a head, because the head is what we will use to remember the rest of the nodes. When we look at the operations on nodes, you would see the importance of the head. But for now, just know that you need to also declare a head. We could have added it just as we've done it here. Then after declaring the node, you need to make space in the memory for that specific node. So this node A, we are making space for node A. Node B2, we are making space for it. Node C, we are making space for it. After we have done that, we now have to assign data values to each of these nodes. After assigning data values to the nodes, we now assign addresses to the node. So this is how we create what? A node, or I mean a single linked list with 3 members. This is how we create it. The next thing which we will look at before we end today's session is, now that we have, yes, any question before I go?
The address parts, I think you have mistakes.
Oh.
Yes.
Mm-hmm.
You said node next, node B, then node C next, node C.
No. This should be node B. Then this should be node C. We get it. So this is the right one. Node A next. So node A what address is node A pointing to? It's pointing to address of B. What address is B pointing to? It's pointing to address of C. And what address is C pointing to? It's pointing to now, because that is the end of the list. Yes, so I hope that is sorted out. All right, the last thing we need to look at before we break for today's session is to look at how do we assess the members of a linked list. So what we have done right now was creating the linked list, creating it, and those are the 4 steps, the steps that I talked about. Why are you no? Okay, so these are the, oh, where was it? These are the steps that I talked about on how to create a node or a linked list, how to create a linked list. You follow these steps. But now our interest is in, after we have created the linked list, how do we assess the members? What we call traversing them. Okay, moving from one element or one item to the other. How do we do that? Okay, before you can assess any member, you always have to start from the head. And that is one disadvantage of linked lists. When you compare linked lists to arrays, one disadvantage of linked lists is that you can't randomly pick a member of the list. No, anytime you need any member of the list, you have to start from the very beginning. Okay, so later we'll learn about some other data structures. Some is queue, star, like those things, and you realize there's the implementation of linked list in there. Linked list implemented in there. Even graph too, I think it is implemented in there. So that's why I'm saying it's important. We need to understand these things because we are going to be using them more often. But the disadvantage I'm talking about is that we know that for array, if I have an array of integers, say 1, 2, 3, 4, 5, I can just call, let's assume this integer is called V. This array is called V, okay? I can just call V index 2, and that will give me 0, 1, 2. Will give me this value. So it's easier for me to access any member. So if you put arrays and linked lists or singly linked lists on the same platform, and I need to make a choice, and for a program I'm developing, but the program that I'm developing, I am looking at being able to select quickly any item that I want, then linked list is not the data structure of your choice. So you see, arrays are not all bad. You can't say arrays are bad. You need to know how to use arrays. They have their own advantages. Quick selection. Anytime you need to select something quickly, you can use an array. But then we also learned that anytime you need to do fast insertion, fast deletion, inserting at the top or something like that at the end, arrays are not your data structure of choice. Okay, so there are a lot of advantages and disadvantages with each data structure we are going to look at. And that is what will guide you. The disadvantages and advantages is what will guide you to choose the right one. So when you're building your programs as a software engineer, you're supposed to think through all of these things and make a choice. No, I need to use an array in this case because I'll be searching a lot in this particular excuse me. I'll be doing a lot of searches, so I need to use arrays. Or no, I'll be doing a lot of insertion. I'll be doing a lot of deletion. So let me use linked list. Okay, the other advantages that you should probably read around. But what the point I'm making is that for a linked list, we always have to start with the head. Okay, so this is how I usually implement or illustrate it. I do this, then so with the one that we have created now, this is what it will look like. Okay, this is A, B, C. Hence, if we are going to go and access each member and print it, what we need is first the head. Okay, we need a head, then the head will help us print what is here. Then after we've printed what is here, we'll now print what is here. Then we'll now print what is here. We are interested in printing only the edges that each of them contain. Okay, so when we are coding, how are we going to get that? Remember that the head will always have to be at the front, so we can't move the head, but it is the head that will help us move around. For that matter, to be able to move around, always we'll introduce another pointer that we are going to be using to move around. Okay, very important. We are going to be introducing another pointer that will help us traverse our list. It's like that pointer is the counter or is the police inspector. So it starts from the head. It asks head, who do you point to? So we are doing investigation. We are looking for somebody. Who do you suspect, or who do you know? Who did you see? The head will say, oh, I saw Ima. Then this one will go to Ima and ask, Ima, who did you see? Then Ima will say, oh, I saw Tony. Then we'll go to Tony. Tony, who did you see? Oh, I saw Gifts. Okay, so this is not part of the node that we have, it's not part of the linked list we have created. We are just creating a temporary pointer that we'll be using to inspect each item until we've gotten what we want. And in fact, in this our case, we want to print each of them. So let's see what we are going to do. The first thing is that we want to check that the head is not pointing to now. If the head is pointing to now, then there is no linked list. Remember, the end of a list is what the end node always points to now. So if head is pointing to now, it means that we don't even have a list in the first place, because head will always have to point to the first node. So it is mostly necessary for you to check that your head is not pointing to now, because as soon as your head is pointing to now, you don't have a list. Very important. So once our head is not pointing to now, which we can assume here because we have assigned node A to head, and even that one, our code can still return head equal to now if malloc of node A fails. Assuming there is no enough space in memory, this is going to fail, and we haven't given any checks. So I mentioned that when you are writing the code, you're actually supposed to check that this is not returning now before you even let it go. But let's assume that everything is working. Now we are going to create the temporal pointer. Okay, so let's say create a temporal pointer. That will be called, is of type structs node pointer called temp. Okay, so we are just create. You can call these things anything you want. It's not compulsory. Some of them are just generics because it's easy for everyone to understand. If I write temp in my code and you come and see, it's easy for you to appreciate it that, oh, this is just a temporary pointer that I've created. Otherwise, I could have called this pointer Obed. But it wouldn't make sense to you. What is pointer Obed? Okay, so that is why sometimes we stick to some of these ones. Now we know temp. Before we start, we are going to start traversing the list. That means we have to start from the head. So temp will have to first go to head and ask head, who do you point to? So the first thing temp will do is who head points to. Remember, head is what? A pointer pointing to what? Node A. So in fact, by saying temp is equal to head, in actuality, what you are saying is temp is equal to node A. Remember that. But we always start with head. So we'll just say head. Temp is equal to head. But don't forget that head is a pointer that points to the first node, which in our case is node A. So it means that temp here is also pointing to node A. Okay? Then once temp is pointing to node A, it means that we can get this node B. How can we get node B? By just doing temp next, because we know that node A, which is the first one, The next one is node B, points to node B. So if we do this, we will get the next one. Don't forget that. Let me come again with it. Even though I've written here temp is equal to head, you should remember always that head is just a pointer. Head is not a node. It's just a pointer to the first node. So in essence, what I've said is that temp, I am assigning you to the first node because this is just a pointer to the first node. So head is not a node. So the moment I do temp is equal to head, all that I'm doing is I am now assigning where head was pointing to temp. So temp is now pointing there. Once I have that one, I can get access to the elements in node A. So if I want to print what is in node A right now, I can just go ahead and say temp, then age. If I print this, I'm going to get the age that node A is storing because I've assigned the address that head is pointing to. And head is pointing to node A. Okay? Head is pointing to node A, so I can access it with this. So what we can do is, since we are interested in printing each of them till we get to the end, what do we need to know? We need to know that at the end node always has its next pointing to now. So our checks that we are going to check, the first check we are checking is while temp next is not equal to now. Very important. So any other thing that we are going to, this is how we traverse the linked list. So let me write it here. Traversing the linked list and printing each member. This is how we go about it. There are interests. That's why when we started, I said we should pay attention to two things, the head and the end node. Because always we will start from the end, the head. In fact, on Friday when we meet, we are going to look at various operations like insertion, deletion, reversing, and searching, and all those things. And for each of these, we need to know how to traverse the list. That's why it's important. We need one to know how to create the list. That is what we are doing today. We've created a list. We need to be able to traverse the list because in some cases, the list will be given to us. We have to traverse it and do what we want to do with it. So those are like the two basic things that we need right now. How do you create a list? How do you traverse it? Traverse basically means how do you move along that list or find each member of the list? And that's what we are doing. And I've said that we need two things. We need a head and the end node. The head is just a pointer to the first. So ideally, when I say the head, it's like, oh, I'm showing you where the first is. Once you find the first, you can now find the next one, which will be the second. You can find the next one, the third, and that. So what I'm saying here is that my temp here is now equivalent to head. That means my temp now points to the first item. So when we get into the first item, I want to see the first item. What is the next address you are pointing to? If that is now, then it means I've gotten to the end of my list. But for as long as I've not gotten to the end of my list, I want you to do something for me. So what do I want you to do? For as long as you are not the end, I want you to print. So let's say print f of %d, because the 8 is an integer. Then let's just map it to the next one with this. I think then the value we are going to pass here will be temp age. Great. So the first time we enter this loop, obviously, this is not now because we are now pointing to node A. Okay, we're pointing to node A. So if I get in here, what I'm doing is I'm printing node A age. Remember, right now, because I've created this, you may think that, oh, I know node A, so why am I not calling node A? The thing is that in the ideal case, you don't even know that there is a node called node A. You don't know that there is a node called node B. You don't know that there is a node called node C. The only thing that you have access to is head. Don't forget that. In the real case, when you are dealing with linked list, the only thing you have access to is the head. You don't know where the end node is. You don't know how many members there are. So I can ask you, I've given you the head. Find how many members are in this list. Or now I've given you the head. Go ahead and print all the members of this list. So you have no idea what is there. If I knew these ones, why would I even bother myself using a loop? I'll just come here and print these ones because I was the one who assigned values to them. Okay, don't mistake that. This is just relearning. We learned how to create the list. So assume the list was created already. It's available in memory. All that you have is the head. Now they say print the members of this list. This is the head. We've given you the head. Print the members of the list. That's what we are trying to do now. So the first thing we do is we create a temporal pointer. Then we assign that to head. This is going to run through almost everything we are going to do. Always, because we start counting from the head. That is the first one. We take it from the head. Then we go one by one. So the first time we enter here, we check, okay, this is pointing to head. Head is a pointer, not a node. So you can't say that it's pointing to head. It's pointing to the address that head was pointing to. So ideally, temp is now pointing to what head was pointing to, which is node A. So temp is pointing to node A. So here we are checking that node A next. Is it now? No. If node A next is not now, then remember temp in our case is node A. Then we want to print node A age. Okay? And after we have printed node A age, how do we move forward? We move forward by reassigning temp. Temp, I said, as a police officer, when temp went to head, he asked, head, where do you point to? Head says, I point to Ima. So the police went to Ima, and now Ima has produced what he has. Okay, he has given it to the police officer, so he has seized that one. Then now he asked Ima, who else was with you? Ima said, Tony. So the police officer now has to move to Tony. So the police officer in this scenario is temp. Temp was originally with what? The node A, or starting from head to access the first node. Now it has to move to the second node. So how do we move it to the second node? Remember that this temp next is actually the second node, because temp here was pointing to the first node, which head was pointing to. So as soon as we call temp next, we are pointing to the next node after the first node, so the second node. So this temp here is the second node. So the temp next is the second node. So if we want to now assign temp to the second node, then we have to do temp is equal to temp next. Don't confuse the two. That's what confuses a lot of people. Please don't confuse it. Let me take it over again. So what is happening here is you are just creating a pointer that will be traversing the list. It will go one by one and go and collect each of them, the items. So I'm giving an example, assuming all of us here went to steal something. So it's a linked crime. And they've assigned a police officer that, oh, this is the head. Obed is the head of that group. So go after Obed. The police officer is 10. He has come to me. He asked me, Obed, as for me, I was the head. I called the shots. I didn't steal any of them. I don't have any of the items with me because I'm not a node. Head is not a node. Okay? So all the other members are the ones that are nodes. They contain items. So when the police officer came to me, I gave Ima out. It was Ima that I sent. Okay, so Ima's address, I gave it to the police, and the police went to Ima. This is what is happening. As soon as the police came to head, he got Ima's address. So this is temp to Ima. Ima is our first node. Okay, so if you now call temp next, it means who is next after Ima. That is what we are trying to do here. So Ima gave the address of Tony. That means that Tony is the next person. Okay, so by saying that this police officer, the first time he came, to see head, we point it in the direction of Ima, so he went to Ima. Then, when we enter the loop, now we are trying to reassign the value of temp. We are giving a new address to the police officer. Remember, the temp is the police officer, but this temp next is the address that Ima gave the police officer. So now we are reassigning, okay, police officer, now go to Tony. That's what we have done here. So it will go to Tony. When he gets to Tony, temp is now Tony. That's the second member of the element. Then we are going to check what Tony is pointing us to. Is it an empty one or there's someone there? If it's someone there, then I have to go inside and print it. Then after printing it, I reassign the police. Go to the next person. So that's what is happening here. Please, this is like the basic thing you need to understand for the rest of the things. To appreciate the operations, you need to understand how this movement is done, how we use a temp to traverse. The first time you give it to head, remember, once you've given it to head, it means you've given it to the first, you've given the address of the first node. With the first node, you can access the second node by just attaching pointer to next to it. So as soon as you write, anywhere you see something, let's say if I write temp and I write temp next, it means that what temp is currently, the next one is temp next. Okay, so now I want to reassign a value of temp to what it was the next of temp. That's what is happening here. Let's go ahead and print, run this program and see what we get. So hopefully, if everything is working all right, we should get it printing out. Oh, no. We should get it printing out all the values that we gave. What were the ages? Let's go and check the ages. Then remember, I did an arrow like this. The arrow is just to show that we are pointing. This one is pointing to this. So we'll get to see. The ages. Okay, so we have 67, 47, 35. So if everything goes right, we expect to see those ones. Then let's compile it to node. Great. Now run node. You see what we have? Oh no. Where's 35? So 35 didn't come. Then we have to go and check. 35 didn't come. So that is one thing. Let me see. Once we are checking that it's not now. As soon as we get to C, remember, as soon as we get to node C has this. So one way that we can solve is, once we have gotten that, it means that temp now is temp now is node C. So we can go ahead and print it outside here as well. There are several ways to go about it. You can go ahead and print it here. Because now, by the time this loop is over, we would have gotten, how do you call it? By the time this loop is over, we would have gotten to temp as node C in our case. So temp node C, the next of it is now. That's why it's not printing it. Therefore, when we come here and we print age of temp, it should add that to us. Let's recompile the code and try it. That should work. Recompile and run this. Good. I should break this thing here. So I hope you are getting the concepts. It's very important for the operations, because the operations are the more important parts, but you need to understand it so that you will do the operations. So this is what you can see. We have 67 pointing to 47, 47 pointing to 35, then 35 pointing to now. Okay, so this is how I was able to traverse the list and print out the members of the list. Any questions? So we are done with the theory. Any questions? Next time we meet, which hopefully will be Friday, we'll look at how we can delete when, like, there are various operations that, especially deletion and insertion. Okay, inserting members into the list and deleting members into the list. Remember that I said one advantage of linked lists is the fact that they can easily, like, you can fastly insert, like it's fast insertion, fast deletion. Okay, so those two operations, if you don't learn any operations on linked lists at all, you should learn how to do insertion and how to do deletion. Because anytime you're working with a project that you think you need fast insertion, fast deletion, that is one of the options you'll be looking at. Okay, but there are other things like searching, which is not the best when it comes to them, but we still have to know how to search. Okay, we still have to know how to reverse the list when we are given, because we've learned how to reverse an array, all of those things. But these ones, especially the traversing part, which we did later, is the most important or the basis of all of them. So if there are no questions, then we'll bring the session to an end here. And hopefully Friday when we meet, we'll look at the operations, most importantly, insertion, deletion. How do you insert at the beginning? How do you insert at any point in the list? And how do you insert at the end of the list? The same will apply for deletion. How do you delete in the front, any part of it, and at the end? Then we may also look at other things like selecting or searching, sorting, reversal, and the rest. But as I said, the most important will be selection and insertion. So those will be my primary focus when we come back, God willing, Friday. If you don't have any questions, thank you for coming, and I'll see you on Friday.
Thank you.
Bye-bye.
Thank you, Doctor.
All right, time
You're
Friday.
welcome.